Hello and welcome to this video. My name is Aniruddha, Victor Uniform 3 Foxtrot Mike Lima. In this video, we are going to design, build, and test a J-pole antenna for VHF. That's 144 megahertz to 146 megahertz for hams over here in India. So I've fired up the mmana -gal basic software, and let's go and enter the name VHF JPOL. You can enter anything that you like, no problem. The frequency for which we are going to design this antenna is the center frequency, oops, 145. So that's what we entered here. Let's go to the calculate tab. We are going to put this antenna up at 3 meters and we are going to make it with copper pipe. These things can be changed afterwards as well. So let's go to the wire editor and let's select XZ plane, and we will start uh, making the antenna. However, we need a starting point, and we can use formulas for that purpose. Most of the hams use this site called m0ukd.com, and there is a JPOL calculator. So I've entered 145 megahertz. This is the velocity factor for the copper pipe, and once you calculate it, it gives you these dimensions. Uh, the A, C, and F are the ones, and D as well, are the ones that we are going to look for. Um, F is not that critical, but we should definitely look for A, C, and D um, measurements. So here they have given that A as 149 centimeters. So that's this. So it includes the half wave element and the matching quarter wave section. So the complete length is suggested to be 149 centimeters by this calculator. The other is C, very critical, and it is the quarter wave matching section. So it is suggested to be 49.7 centimeters. The distance of feed point from the bottom is considered to be uh, 5 centimeters, and the spacing F, which is not that critical, is suggested to be 4.5 centimeters. So I'm going to take this measurements and put it in the software and see how this actually performs. Now the only difference is that this calculator has not considered the distance from the ground, so how high the feed point will be from the ground, but that's part of the software. So we will be considering that as well here. So I will just start with, so what was that? It was 149 um, centimeters as the half wave section plus the quarter wave matching section. So 1.49 meters. Okay. So then we draw, let's zoom it a bit, and then we draw uh, the gap between the two elements, and that is suggested to be 4.6 centimeters. So I will just define the wire with 4.6, which means 0.046. Is that right? One, two, yeah, that's 0.046 meters. So I've defined it, and now we need to add the quarter wave matching section, which was 49.7 as per the calculator. And now to draw that, I need to bring this point as a point on one of the grid lines, so that I can draw it easily. And then I have just drawn some length, and then I will define it here as 49.7 as per the calculator. So 0.497, that's right, meters. Okay, so we have drawn the antenna. Now we need a place to put the feed point. For that, what I will do is I will divide this bigger element into two pieces. Yeah. And I will divide this also into two pieces. So divide wire into two pieces. The I need to shift this point to point not 5 meters. That is the 5 centimeter mark from the bottom. So I will just change the wire definition for this and write it point not 5, and it has shifted that point below. Same thing for this side as well, point not 5 meters, and it has shifted down here as well. Now um, I need to add a line between these 2 points, but it will not allow me to do so because this line is not on any of the grid lines. So what I need to do is now just shift this point to one of the grid lines, and then I can just zoom a little bit more, select this, and then join it here. That's better. So if you see, it is 0.046, so that is 4.6 centimeters. So we got that right. If you go and look for this antenna here, let's select X, Y, and Z, and then zoom it. So we have this uh, wire going from between the two elements. Yeah. So now we need to add a feed point at the center. So add source to the center of wire. So we got the feed point over here, and that is our antenna. We need to check this now for its performance. So if we go to the calculate tab, frequency is 145 megahertz, height is 3, the material used is copper pipe, and we have used the exact dimensions that were given to us by the calculator. I'm going to press start, and you see here the SWR is quite high, right? If I go to the plots and then go and check for the resonance, let's see where it gives. It is on the higher frequency, 146.33. We want it at 145. So if it is resonant at a higher frequency, let's leave SWR aside for a minute, but it is resonant at a higher frequency, and we want it to lower it, which means the antenna is shorter and we need to add length. Now, I've done this before, and to save time, we will just go to the optimization and select SWR and take the slider to the right hand side, which will prioritize the SWR and uh, change the dimensions of the antenna to make it match perfectly. I will select all elements and then just press start. It will do its calculations, and then if you see here, it is already at 1.02 SWR. The impedance looks good. It has done its calculations, and it has decided what should be the ideal lengths of the elements. So right now the elements have changed their lengths, and we'll go and find out what are the changed lengths. So let's start with the quarter wave matching stub. This one is 0.447 plus 0.05, and that comes out to be 0.447 plus 0.05. That's the feed feed point length from the bottom. It comes out to be 49.7 centimeters, which matches exactly with what the calculator had told us. The distance between the elements is 4.6 centimeters, which was again suggested by the calculator. Um, so what has changed that made this possible? Because we had initially put all the same readings from the calculator. So it was this length. Here you see 1.558. And if you add 0.0528, it comes about to be 160.8 centimeters. So the calculator has suggested us 149 centimeters, but the software is telling us that it should be 160.8 centimeters, uh, the bigger element. So if we go and calculate it once, it shows a good match. And then if you go to the plots and then check the resonance once, it is bang on 145 megahertz, and the entire range is having a very good match. So the calculator which everyone uses, it's giving a good starting point, but the software is showing me something else. The length of the bigger element has to be 160.8. That's what the software is telling me, instead of 149 centimeters, what the calculator told. Let's go and check once for the far field plots. So here you can see the gain, if that matters, is 4.5 dBi at 6 degrees elevation angle. Go to the 3D. So this will be the radiation pattern. And if you have observed, there will be a little bit higher gain towards the side of the stub. So if we go back again here, you can see here, this gain is higher than the gain on this side. So, and this is the part of the positive x-axis. So if you go and check, the stub direction is on the positive x-axis. So it gives more gain in this direction, the software tells me. Okay, so another thing that we have observed is having a mast. So let's just draw a mast over here. I prefer it to be 1 meter, that's half wavelength. And I just press OK. So this is the familiar looking J-pole antenna we all are used to seeing. Um, what will happen after we have added the mast? Let's go and check it one more time. There's a little bit of change in the SWR. The matching remains still good. Let's go and see the far field plots. The gain seems to have improved. So at elevation of 6 degrees, from 4.6 that we saw earlier, it's now 5.5. People say that anything below this short does not matter, but if you see, the software tells me that there are R currents in the mast, something to consider. All right, so this is the designing of the J-pole, and now I'm going to use the exact same measurements that the software is telling me and build that J-pole. So hang around, we'll get to it. So this is the finished J-pole antenna for 2 meters. As we saw in the simulation, uh, this length up to this point is 160.8 centimeters, and this portion over here, the matching stub, is
according to the design, it is supposed to be 49.7 centimeters, and then I've added about 100 centimeters of mast from this point onwards, and this is the way I've attached the coaxial. The center core goes to the longer element, and the shield goes to the matching stub. Right now I have attached just SO239 with short piece of cable, and then I will attach the main coaxial cable to this. um, I could have directly attached the cable here, the one which I'm going to use, the coaxial cable, or I could have soldered this SO239 here, so that the shield connection is made, and then from the center pin uh, I could have soldered the center conductor over there. So I'm going to try with this setup. Now the only difference between the design and the actual is that the design says this matching stub has to be 49.7 centimeters. I already had installed this antenna last night, and I found out that that length of 49.7 centimeters is a bit too high, so I had to cut off a couple of centimeters. So now it is 47 centimeters from this point onwards till the end, that is 47 centimeters. Other than that, this length is 160.8, which is same like the design, and the distance between the two is 4.6 centimeters, just like the design. So everything else remains the same, and I'm about to mount this antenna uh, over there near that pipe. This is the highest point of my house.
So this is how the antenna looks after it has been installed. I have added an air choke. This is about 5 inches in diameter and about 5 turns of the coaxial cable. I'm using LMR 200 cable for this purpose. Another thing that I've done is I have weatherproofed the connections. I've used a rubberized tape which is used to seal the electrical connections of a submersible pump. So at this point, and at this point, I've applied that tape to make it waterproof. So I've connected the antenna to NanoVNA, and this is the VHF frequencies from 144 megahertz to 146 megahertz, and right now the marker is at the center of the band, that is 145 megahertz, and you see that the SWR showing is 1.2, and the impedance is around 47. If you see, the lower end would be around 1.1, and the upper end would be around 1.35. I think that's acceptable range. So I've connected the antenna to my base station, and let's see what is the actual SWR that we are getting when I transmit. This is Victor Uniform number 3 Foxtrot Mike Lima. So it is around 1.19 on 144.8. I think it's pretty good. Let's see if I am able to make any contact using this setup.
This is Victor Uniform 3 Foxtrot Mike Lima. Is there anybody on the frequency? Over.
Victor Uniform 3 Foxtrot Mike Lima. This is Victor Uniform 3 Yankee Echo Kilowatt. Copying you 5-9 at my end. Great signal. No QRM, no static whatsoever. How do you copy me, FML? Over to you.
YKFML, I'm copying you 5-9 as well. Good signal from you. Again, crystal clear copy. No problem at all. This is the new J-pole that I've installed, and transmitting about 8.5 watts. The SWR is 1.1 approximately right now. Good copy from your end as well. What is your setup, please? Over.
FML, this is YK. Current setup is a Diamond X50 antenna with a UV5R. So transmitting at about 3 to 4 watts at best. Over to you.
Great signal from your end. So yeah, I'm testing this J-pole for the first time. I just installed it. It's about 15 feet max above the terrace, and so I wanted to test. Thank you for coming back to my call, YK.
FML YK, this is wonderful. Seeing that we have a good distance between us, and also I think there are a few hills. So getting VHF 5.9 on simplex in an urban environment is, I think, wonderful. Kudos on the new antenna. Looking forward to your video to learn more about how you made it and getting more details about that. Otherwise, great signal. It's wonderful that we can have VHF simplex. I think this is the best QSO we've had on VHF simplex so far. Over to you.
YKFML, thank you very much, YK. Great to talk to you. So 73 is to you, and we will catch on VHF again some other time as well. Thank you for coming back to my call. This is Victor Uniform 3 Foxtrot Mike Lima.
Victor Uniform 3 Foxtrot Mike Lima. This is Victor Uniform 3 Yankee Echo Kilowatt. Right, 73 is. Thank you once again for the wonderful QSO. Have a great Sunday and a great week ahead. See you on the air soon. Wishing you 73s.